Generally, students don't want there to be curves thrown on their test. I think this is a bit of a curve. But I'm not sure it asks what you think it asks. Meaning, we have two different accelerations. In fact, there's a horizontal acceleration of 2 meters per second squared. The object begins at the origin, has an initial velocity of 0. So if I was interested in the displacement of the object horizontally, I could say that x minus 0 equals 1/2 a t squared plus 0t. That's a function for the horizontal position of the object. But it's a function of time. And they specifically say that we're supposed to have a function that does not have time in it. So what else could you do? Well, we need something about the y direction. And folks, you don't believe this, but I've trained you how to do this. This is a projectile. Solve for t in one equation and plug it into the other. That's what this is. That will eliminate t. The acceleration in the y direction is negative 1.5 meters per second squared. Its initial position is 2. Its initial velocity is 0. So similarly, I could have y minus 2 equals 1/2 times negative 1.5 t squared plus 0t. Any questions yet? Now, this is what I think all of you could have put together. These are the motion variables. This is the motion stuff that's there, which gives me x equals t squared from this, and y equals negative 0.75 t squared plus 2. By the way, this is what's known as a parametric equation. It's two equations that are based on the same variables. But substitution, t squared equals x. So y equals negative 0.75 x plus 2. That's linear. Y equals mx plus b? Linear. So let's see, the y-intercept is 2. And it has to be a straight line because it's linear. That has a slope of negative 0.75. Be careful. The scale on this side isn't the scale on this side. So you got to be careful about that. So like I was trying to use negative 3 over 4. So when I do that, down 3 over 4 doesn't work, so it's over there. So I went down 1.5 and over 2. That kind of gives me what my line should look like. But you can't stop it there. You have to continue the line because the box goes all the way to the ground. So it should stop when it hits the x-axis. Because it's not like the box can go underground. Now, there's another way you could have found out where to stop the box, where to stop your line. You could have solved for the x-intercept, which means solving this for x and seeing what you get as your extra number. You get negative 2 2/3. 2 2/3. Now, what's really hilarious is that I don't know how many students could actually do that. It's not hard when you see it. But in 15 minutes on the AP exam, I think many students probably didn't get the credit here. I don't have data from this test. It's pretty old. But I bet students were like, screw that. I'm going on to the next question. I have no idea what they're talking about. That's what's on a practice test. Yeah. I think that if you can do A, B, and C, you're probably in good shape. I think you could probably set up D. I think students probably made mistakes on E. But trust me, I looked at some of your work. Many of you didn't make it this far at all. So it's hard to know from your work whether you made it to this point or not, or understand it. Next. No further questions then? All right. Yes, Juan.
Number 25 on chapter, page 6. The answer C got so many things there. Oh, chapter 5, I think.
Narrow it down or flick something at me.
Okay. 25, it is the stubborn mule question.
The farmer is able to move the mule as if he can break static friction. And he is pulling with a applied force of 800 newtons. I'm thinking we've got 800 newtons, friction, normal force, and 1200 newtons, the weight of the mule. We don't know if the net force is zero or not. We do know that friction has to be less than or equal to mu s times the normal force, and I can tell you that friction has to be less than or equal to 0.8 times 1200. The normal force has to be 1200. But the book probably used 9.8 here. But I'm not going to. So 8 times 12. So 96. So this has got to be less than or equal to 960 newtons. So I don't think the mule budges.
That's what the book.
I don't know what the book says. Now, wait. The book might recognize that the farmer doesn't have to pull sideways.
I tried with angles, and I still couldn't get less like.
Okay. Do you want me to do the problem one or not?
Sorry.
You have to ask yourself that question too now. No, I'm serious. I could pursue it. Do you want me to see if the book has just made a mistake or whether there's another way to find the answer?
If the rest of the class would be interested.
Has nothing to do with the rest of the class, Juan. But this time, right now, we'll never get back.
Then yes, please do it with the.
Thank you. If we don't, I'm just going to start uniform circular motion. I will not give you the next class minutes. You guys might want those, but you won't get them. If we assume the farmer pulls at an angle, then that means we have 800 cosine theta minus friction equals, potentially zero. Let's do it this way. Let's assume we have the angle of theta. So we're pulling with 800 newtons at an angle of theta. This doesn't change the weight, but it does change the normal force. Because it changes the normal force, it changes the frictional force. So perhaps there's an angle at which we could do this in order to move the stubborn mule. Friction still has to be less than equal to mu times the normal force, but that now has shifted to being equal to mg minus 800 sine theta. Any question about that? Or where any of that came from? Now, the real issue comes down to, can we pull up enough to break the frictional force to move the mule? Now, from here, it might not seem like we could get an answer, but I think we can. We just need any force to the side. Any force is enough. So is there the potential for us to have any sideways force that will allow it to move? I'm not sure if you guys understand what I'm asking, but we want the net force in the x direction to be greater than ma, or greater than 0. That means 800 cosine theta minus friction has to be greater than 0. Looking at this, I say we just sub it and see if it's true. Let's go ahead and assume maximum frictional force. Make the substitution and see if there exists an angle where that will be true. So 800 cosine theta minus mu mg minus 800 sine theta greater than 0. We have to get theta by itself. So I'm going to move, see what would be the best way to do this. Move this over here. No, mg is still 1200. Mu mg is just a number, right? Yeah, so 800. Yeah, but that gives us cos theta minus 800 sine theta greater than equal to greater than equal to 0.8 times m times 10. Oh, I didn't distribute the mu. Thank you. Like so? So now, like that? All right. So keep going with this. Is it possible to have an angle here greater than this number? And the answer is yeah, easily. This is 800 cosine theta plus 640 sine theta. 0.8 times 800 greater than equal to 960. There's most definitely an angle that will do that. In fact, a whole bunch of them. The question is that you probably don't have a math that will solve for theta. That doesn't mean that you couldn't pick an angle and try. All you need is one. So for all you who weren't paying attention, this is easily an FRQ. There's absolutely no reason not to put it on there, because most of you will stop right up here. And this was a level 1 problem, so most people thought, well, whatever. But no, you could pull at an angle, and there's clearly going to be an angle where you can make that work. And it's not particularly big either. There are methods to solve problems like this, by the way, to deal with the fact that you have these two angles like this. They're not easy, though. To be perfectly frank, they're not easy. But I would just pick an angle and start. We know 0 degrees doesn't work, so start from there. Pick 30. See how big it gets. It doesn't take very much to fail break the friction here. So, all right. Ten questions for multiple choice, 2 FRQs. You're allowed to bring your own equation sheets and use them on the test. They have to be untouched, meaning you can't have written anything on them, but they can be the AP Physics C equation sheets. If you don't already have a copy of them from the last time we had a test, I'm not sure I handed them out or not. And either way, you may bring those. Just type in AP Physics C Mechanics equation sheets. I will have some, but I would prefer not to print out an extra 300 pieces of paper tomorrow if I can avoid it. So I'm probably going to have to do at least parts of A and B to adequately explain part of E. So free body diagram is where I would start, and that's going to produce for us 4 different forces that act in the system. There's the pulling force, frictional force, normal force, and weight. So I got into I kind of dug a hole in my last class. I'm going to try and be a little more careful. I don't know how big to make this force. I just know that's at an angle. I don't know how big to make this force either. I just know that's straight down. I know that together, the upwards normal force and the pulling force that is upwards have to match whatever the size this is. So I'm clearly looking at this plus this to be equal to the weight downwards. Thank you. Any difficulty? Any difficulty?
Oh, no.
Thank you. There's also friction to the side. And I'm intentionally making the frictional force less than the horizontal force because we're told the system accelerates. So if you're being judged on your free body diagram, I would expect it to look something like that. Any questions? You were asked to draw a free body diagram. Yep.
So the friction's less than like the F1 because it's unbalanced when it's moving.
Not because it's moving.
Because it's accelerating.
That's right. That good? All right. Now, a quick run through tells me that net force in the x direction is going to be F1 cosine theta minus friction equals MA1. Using the symbols they gave me. Do I need to explain that? All right. And net force in the y direction, normal plus F1 sine theta minus mg equals 0. All good? All right. So I'm just going to change this a little bit. F1 cos theta minus F equals MA1 and normal plus F1 sine theta equals mg. So these are the two formulas that we get from using Newton's law successfully to get to here. We are told that we pull with enough force so that the box loses contact with the ground. So that means N approaches 0. And if N approaches 0, then friction approaches 0. So that means F1 cosine theta equals MA1 and F1 sine theta equals mg. Now, technically, you could probably solve this for A, and this would be your max acceleration. In fact, they would probably have to accept this as your answer, because you're allowed to use F1 and M and theta in your answer. Except, isn't it just staring you in the face? F sine theta, F1 cosine theta? Should be. Because in this problem, they were supposed to say that you couldn't use F1 in your answer. They just didn't. They should have. It was a mistake on the test. But I'd also hope that you would eliminate F1 here to recognize you get an expression for the acceleration that has nothing to do with how hard you pull on the box, which should seem weird since it's going to matter how hard you pull on the box. But it actually gives us a different expression. So that's what I want you to do. We're going to eliminate the F1 by doing F1 sine theta divided by F1 cosine theta equals mg divided by ma. I just divided both equations. And this gives us tangent theta equals g over a max. So solve this for a max, and you get a max equals g over tan theta, or g cotangent theta. This is I think, an interesting answer. It shows that there is this max acceleration that you get if you pull hard enough on the box. That this is right there at the threshold, and it's more based on the angle than it is on the pulling force. I mean, the pulling force has to be great enough to lift the box, so it won't work otherwise, but it is interesting. But this is actually what they were going for. In the grading guidance, they had to give this credit, and they did, but this is actually what they were looking for. Okay? Sophia, is that good? All right. Yes, ma'am.
So when you said that F was approaching 0 and N was approaching 0, in what context? Like I didn't hear you when you were explaining.
The problem asks for you to derive an expression for the magnitude of the greatest acceleration that the block can have and still maintain contact with the ground. If you pull hard enough at that angle, you could lift the block off the ground. That's what they're saying. So we're trying to find the threshold when it loses contact, and that threshold is as the normal force approaches 0. So to find that actual threshold value, we put 0 in for the normal force. That's the instant that the upward force is balancing the weight without the ground being necessary. So it's not accelerating off the ground yet, but the ground is now providing no force against the object. Now, if the ground isn't providing a force against the object, that means there's no friction, because friction is based on normal force. So both of these forces have to go to 0 in that circumstance. All right? Yes, ma'am.
On chapter 6 of the questions, can you explain to me the proof of that?
Number which one?
24.
In chapter 6, number 24. Bonnie and Clyde are sliding a 300-kilogram bank.
Yeah.
Safe across the floor to their getaway car. The safe slides with a constant speed if Clyde pushes from behind with 385 newtons of force while Bonnie pulls forward on a rope with 350 newtons of force. What is the safe's coefficient of kinetic friction? If I were to just... I'm not drawing a picture, but I'll draw a free body diagram if you'd like. That's what you asked for. It says that Clyde is pushing from behind. So, I mean, the safe is a big box. So we got one person pushing. One person pulling. Is that good? That seems to me that there is a 385 Newton force in this direction. That's the force from Clyde. And then there is a 350 Newton force in this direction. That's from Bonnie. I've stacked them. Usually I like to put them side by side, but this time I've just put them one after the other. That also means that there has to be a frictional force this way, because they say the thing moves at constant velocity. So I know they have to be balanced. And in addition to that, oops. I just need to have some space for the next one, so there. There's got to be a downward force due to gravity. I kind of expect it to be bigger than the upward force. I'm sorry, I expect it to be the same size as the upward force, but I expect the upward force to be bigger than friction. So I needed to provide myself some space to get mg and normal force in there. But they're balanced, so net force equals 0. So I need to make the up one equal to the down one and the right one equal to the left one. You're welcome. You said 47? All right, 47. All right, truck with a heavy load has total mass 7,500 kilograms. It's on an incline. It's traveling at constant velocity, and then suddenly it loses part of the load, and we want to know how much of the load fell off the truck. So here's our truck. And a load in the back. The first part of the problem, the net force is 0. Because they tell us the truck is traveling at a constant velocity. They tell us to ignore friction too, so I'm going to ignore friction. So there's this, I don't know, force from the truck, which is a little bit disingenuous the way they do this problem. They probably should have done it different. Like a cable is pulling a box up the ramp and part of the box breaks off or something. By making it the truck and making the truck rolling, they've really made an artificial problem here. So we're still going to work the problem the way they ask it, but it's a little artificial. I'm only going to draw this out because I feel that because we have a test tomorrow and there's likely to be an inclined plane problem somewhere on it, that I should at least take a moment and run through what I feel is the typical stuff that would have to happen on an inclined plane problem, including the fact that there's going to be 2 components here, mg cosine theta and mg sine theta. And unless you're doing something bizarre, it is very likely that these will be the components that will act in your system. You okay?
What's the other force that's missing out there?
The truck's pushing the thing up the ramp. Yeah. So I think I did pushing force in third period. I said force of truck in this period.
Is that the force of the truck on the mass?
It's the force of the truck on the truck and the mass. Does that make sense? All right. So net force has to equal 0 because the truck is traveling at a constant velocity. There's the force of the truck minus mg sine theta equals 0. That's the x direction. I don't even have to look at the y direction because there's no friction, so I don't need to worry about the normal force. Now, this doesn't tell me anything except it could give me the force of the truck. But I'm at the end. The only other thing I could do is say normal equals mg cosine theta. That's the only other thing I could do. So I can figure out the force from the truck and the normal force, and I'm kind of stuck here. But then they say that after losing the load, the truck continues with an acceleration. Okay, when the truck loses the load, that means the mass of the truck suddenly changes. That doesn't mean that the force from the truck suddenly changes. So now we have this new circumstance where the force from the truck minus m nu e sine theta has to equal m nu a, the new mass of the truck. I think if I solve this and plug it in here, I could work out what the new mass of the truck is. And I have the old mass of the truck. It was 7,500 kilograms. If I get the new mass and the old mass, I bet I can figure out how much of the load fell out of the truck. I'd like to stop there, but if you want me to do more of the problem, I'd be happy to do more of the problem. I don't remember who you asked, right? Do you want me to continue or is that good? This problem is a little disingenuous. If I'm going to give you a question on the test, I am probably going to deal with friction differently than this. All right, so
Got missed horribly. I'm sorry.
are you throwing stuff at me?
I was gonna try to hit the last all thing and then I missed. I'm sorry.
Sorry, this is so boring.
It's not boring. I love to do it. I was doing so
All right, so here we go. Textbook questions are written by grad students who are bored. period. And they don't always write great ones. This one's not particularly well written. But it asked the question I wanted you to be able to solve, which is why it's worth doing. So you're driving along at 25 meters per second with your aunt's valuable antiques in the back of the truck. You see a giant hole that is 55 meters ahead. You're traveling at 25 meters per second. Can you stop the truck in time? You don't know. That's a stupid question. The only choice you have is to assume you can stop the truck in time. That's the only thing you can actually do. Because we know that force is all about acceleration. So if I assume I can stop the truck in time, I can figure out what acceleration is required to stop the truck. Right? This will tell me the acceleration required to stop the truck. 25 squared divided by 110. So 5 point something? So negative 5.68 meters per second squared. The valuable antiques, they are experiencing only 3 forces when you slam on the brakes. Those are the forces experienced by the valuable antiques. Only one of these forces actually can stop them, the frictional force. And the frictional force is less than or equal to mu times the normal force. I could attempt to figure out if, when stopping the truck, I stay within the threshold. Because we have a specific acceleration we have to maintain. For the valuables, the net force in the x direction has to equal ma, which means friction has to equal ma. So friction has to equal m times 5.68. I don't have to put the negative sign in there because I'm going to deal with this formula where I strip away all the direction stuff. So m times 5.68 has to be less than or equal to mu times normal force is just the balance of the weight, mg. So is mu greater than or equal to this ratio? Or textbook question. This ratio. Now, I don't know. What is mu? Oh, they give me mu. The static frictional coefficient is 0.6. So it looks like if you use 10, we stay below 0.6, and the valuable antiques are preserved. 9.8, you better plug that in and see. Maybe with 9.8, there won't be enough friction, and they'll break free and shatter like their hopes and dreams. Still okay? Oh, goody for those antiques. Hint, you're not trying to stop in the shortest possible distance. What's your best strategy? So I guess you could have done the problem that way, where you figure out what the maximum friction the objects could take, and then see what the distance is. But I think this works just fine. Take your pick. There's other ways to have done this problem. This is the way I chose to do it.